Hi everyone, I want to talk about semiconductors today and the chemist's way of thinking, because after all I am a chemist or studying to be one. And I want to talk about the chemistry behind them because they're very, very, very important in engineering. We'll also find in a lot of the instruments that chemists even use, and just in general electronics, they're very helpful. But how do they work? Well, that's what we're going to talk about today. So we have to remember what molecular orbital theory says. It says, for example, if I have hydrogen and a hydrogen atom and they both have an electron, well, when they form a bond, we get this molecular orbital diagram where we fill the sigma molecular orbital and you get a hydrogen sigma bond. Pretty simple stuff, but when we talk about these vast networks of solids, things get a little hairy. So let's take, for example, when we take a lithium, okay? A lithium network solid. So you have a solid piece of lithium, this is what it would look like. So you're gonna have your one lithium, and let's say it binds to another lithium. Well, we know that what's going to happen is we're going to split a molecular orbital. We'll have sigma and let's say sigma star, okay? And that fills up because there's two of them. So hopefully you can kind of see it. And here's the energy diagram. But what then happens if we attach another lithium? Well, then we get further splitting of this. And sorry, I guess I should, there's no real labels I should really use for this, but just one valence electron, you can think of it, and we're making this network solid. So we're going to get all these different bands. This would actually be, I believe, with that. So if we're determining the molecular orbital diagram for this whole system, if we have 4 lithiums in bonding. Now it undergoes metallic bonding, but we are assuming for this model it kind of does covalent bonding, which is kind of an interesting take. But let's say you add so many lithiums, then this thing just becomes a huge network or a sea of metal atoms. So let's say this lattice just goes crazy to infinity, basically, or a number comparable to infinity in the reference of what we're talking about. So many, many, many atoms like we observe in the real world. Well, what we're going to notice is we're going to get this blending of molecular orbitals. We're going to get so many different molecular orbitals. We're going to get what's called a band, and this is the idea of band theory. So I'm just going to draw this, and then we'll get into that. So eventually you get this band, right? You get so many molecular orbitals, just like a band, kind of like if you've ever done a column chromatography, kind of like that. It's in the way that it looks. And what you get in a conducting species is you get this lower band, and in this band you have electrons. You have electrons in this band. So there's electrons here. And specifically at the top here, we have a HOMO. And if you remember what HOMO means, it's highest occupied molecular orbital. That's going to be where the HOMO resides, at the very top of the band. Now what you also have is this non-electron density filled band, which we'll draw in red. And this is the LUMO. Okay, so this is the idea of band theory, and it's where the explanation for semiconductors comes from. But it's really this simple, is that when you have network solids forming together, even like, for example, if you have carbon, like graphene, diamond, you know, those big carbonous, you know, ring plate, you know, all those weird structures that you've seen, you get this kind of system to it. But there's one thing we have to recognize. It's, well, what if the HOMO and LUMO aren't equal, right? In this example, I drew it such that there would be an equal HOMO-LUMO gap, or such that there's no gap there. But something can happen, and I'm going to erase this, so if you need a picture or notes or anything, definitely write that down. But of course, you can just rewind. But sometimes when these bands are formed, they have a gap, and that's the HOMO-LUMO gap, kind of like we see in our molecular orbitals, just with these huge network solids. And we can get three kinds. Well, we can get what we saw initially, right? Something like this, where we have no gap. So if there's no gap, this is a conductor. And why is this? Because if an electron comes into this network solid, it can easily be incorporated to the LUMO without having to need sufficient energy, right? It can just jump right into those molecular orbitals. However, if there is a gap, and a significant one at that, if there's a significant gap, well, then it's an insulator. Okay, so if we look at how this looks, if we have a huge delta E here between the electron dense band and the electron deficient band, well, imagine an electron coming in here, right? We want the electron to be incorporated, but it would much rather reside down here, but to do so, it has to jump up to this really high energy LUMO, and that's just not very feasible for an electron to do that. So this is where insulators are coming from. However, something interesting happens. What if, for example, we had a gap that wasn't very big? Say something like this, so a smaller delta E, okay? Well, we're still gonna have our electrons jumping in here, but we'll also have our non-conducting band. And what can happen in this is we say the gap is meh. It's meh, you know? It's whatever, it's small. That means when an electron comes in, it's not going to suffer as much, oomph to get into the LUMO. It's really just like, okay, I can kind of jump up. They're not as good as a conductor, but, it can jump up if it pleases to, more so than an insulator, but less so than a conductor. And then we call these, of course, semiconductors. Okay, so this is a semiconductor. Okay. So now that we have that out of the way, I want to discuss with you the different types of semiconductors, because this is where we really care about. They have different conductivities, and a semiconductor isn't as conductive, but not so much an insulator. It's in the middle. It's primarily helpful in electronics. It can give desirable conductivities. So let's talk more about them. The P and N type conductor. Okay, so we have two kinds of semiconductors, and my notes fell down. I want to make sure I have those. We have a P-type semiconductor. We also have an N-type. Okay? So what's the difference? Well, P stands for positive type, and N stands for negative type. And it comes from how many valence electrons are in that semiconductor. And how we make this P-type, N-type is what we're going to do is we're going to tweak the semiconductor. So let's say, for example, we have silicon, okay? So silicon will make this nice network solid. Okay, so let's just say this one, for example, and it has some band structure like this. So a semiconductor that is neither P-type or N-type would just be the pure elemental form. To get P-type or N-type, we have to contaminate, literally just contaminate our semiconductor. But let's just say we have a pure one, okay? So let's say it looks something like this, okay? So not a very sophisticated image. And let's say the band gap is that much, okay? All right, so if we have a positive type of semiconductor, that means that we're going to deplete this HOMO. So what's gonna happen is, if I can draw it here, same exact energy gap, but let's say in the silicon lattice, we now put, and let me just make sure that you guys can see this over here, okay? Silicon, we have silicon, we have silicon, we have silicon, but let's say in this case we put gallium. So if you know on the periodic table, it's in the same group as boron, so it's 1 over to the left of silicon if you look at a periodic table. That means that it has 1 less valence electron. And if we kind of look at how this network solid would continue, maybe some bonding like that, while the rest of the silicons are doing this, they are making 4 bonds, while gallium is only making 3. And because of this, it's going to drop the conductivity. I just draw the structure here. And sorry, I misspoke. It doesn't drop the conductivity. It drops the amount of electrons in the HOMO. It lowers the HOMO. So now the HOMO drops to here. And what happens is now we have some of this red region, or remember that's electron deficiency, and we now can allow these electrons to jump onto our band, so to speak, or into our lattice and conduct. So positive type is going to allow rapid conduction, as we'll see. Okay, let's talk about N-type semiconductors now. If you can kind of follow what gallium, the gallium impurity did, right? It had 1 less valence electron. Well, what do you think N-type does? Well, you add a valence electron. You could, for example, use, let's see, maybe something like phosphorus, arsenic, for example. In this case, we'll talk about, we will do, let's talk about phosphorus, okay? So N-type, you have these silicons. Let's say now you have a phosphorus. You have 2 more valence electrons in the lattice. Okay, that's of benefit because what's going to happen is in our band structure, okay, if we look at our band structure, same gap, but now you overfill the band and you promote it to the LUMO, okay? So now it jumps up, you still have a depleted region, but now the LUMO gets filled and you have some electron density over here. And that's where these P and N type semiconductors really come from. And you might be like, well, what's the point of this? Well, being able to manipulate these bands, like having a really high conductivity or having kind of like an insulating ability, or maybe just having none at all, just being a kind of a semiconductor, is going to lead to some helpful things. Now, let's look at just one very rough kind of application of this, known as the PN junction. Okay, so the PN junction is used in electronics to allow for differing abilities, which we'll see. Okay, so in a PN junction, you're going to have a P-type semiconductor exactly butted up with an N-type semiconductor. And what happens is, here is our junction. What naturally happens because of diffusion is we're going to have, well, let's say in the P-type, we know we have more positive charge. So here's it before diffusion. And we also have a N-type, which has excess negative charges in it. Let me just expand this a tad. Okay. And what happens after some diffusion, right? Charges diffuse across. the p-n junction, you'll get something like this, where some of the positive jumps over and some of the negative jumps over. And this effectively will act like an insulator. So this is an insulating region. Okay, and that has various practical applications, but one thing that we can do is hook this thing up to a circuit. And the notation, if you recall from your physics course, looks something like this, where we have this. Maybe you've seen this before, maybe you haven't. This is a p-n junction. And let's look what happens when we apply a voltage across the two. So say something like this. Oh, and by the way, the notation is that this is the n-type, right? I just want to make sure. And this is the p-type. So we have p-type side, n-type side. So kind of important we draw it. But let's add a positive bias on this side and a negative bias on this side. This is n-type, this is p-type side. Well, what's going to happen at that level is that, think about what's happening. We have positive charge pushing on the p side, and it's going to push some of that negative charge back, and we're going to get something like this, where we get a widening of the insulating region on that semiconductor. So maybe something like this, and that has practical application, shortening the insulating region. But then also, what you can do is, let's say you hook up the circuit, what happens if you reverse the bias? Okay, so now you have negative charge. Well, what's going to happen? Okay, you have your band. Well, now the negative charge is pushing on some of this positive charge, which allows more of it to go over. And so now you have an even bigger insulating gap. And all this stuff is used to control things in a circuit. Now, to be fair, I'm not very knowledgeable on this stuff, but I wanted to point out what happens when you apply voltages across p-n junctions. This is the important applications that people studying electrical physics is going to be concerning themselves with. But that's really all I have to say about semiconductors. They're very interesting stuff. If I can think of anything, maybe I'll add a little bit to this. But remember, you have this infinite amount of molecular orbitals that you're forming, such that we can describe it with a band. If the band gap is large, we call it an insulator. If it's small, we call it a semiconductor. If it doesn't exist or it's negligible, we call it a full conductor. We have doping, and in p-type, remember, with the n-type, that stands for negative. We're adding impurities that are higher in their valency. So they kind of donate electrons to that semiconductor. Whereas if we have a p-type, it's the opposite, less valence electrons, more positive charge, or holes we call it. And that's going to kind of deplete that HOMO layer. We also looked at an example of a p-n junction, as we just saw an application of semiconductors that can be used in some sort of electrical application that I wanted to share with you. So that's going to be it. Hope you have a wonderful day. Bye-bye.